we have now seen two examples of recursive functions, factorial and sum of digits. And for each of these examples, we have seen two versions. A version based on a simple mathematical definition and a version designed with invariant programming. And we can see that the second version has two interesting properties in both cases. First of all, it has two arguments, one more than the simple version, and one of the two accumulates the result, and we call it an accumulator. Also, the second version has a property called tail recursion. It means that the recursive call is the last operation in the function body. So what can we learn from this? Well, let's take a closer look at tail recursion. Let's in fact do a detailed comparison of fact1 and fact2, the two versions of factorial. And in fact, this comparison is a first step toward the formal semantics that we're going to see in lesson 6. So we will see why fact2, the version with tail recursion, is in fact more efficient than fact1, the version with no tail recursion. So writing your program based on a simple mathematical definition is in fact not the right way. The right way is to design your program with invariant programming. So let's take now a closer look, comparing fact1 and fact2. So remember tail recursion, the recursive call is the last operation. Let's take a look at fact1 first. Fact1, in the function body, we have n times fact1 of n minus 1. Notice that after the fact1 has finished its calculation, it has to come back to do this multiplication operation. Which means that during the calculation of fact1, the multiplication has to be stored somewhere in memory. The system has to remember that it has to do it. And where is it stored? In fact, it's going to be stored on a stack. And we'll see why, because many multiplications will have to be stored. In the other version, we have in the function body fact2 of I minus 1 and I times a. So the last operation is fact2. In fact, after you do this operation, nothing more has to be done in the function body. It does not come back. In fact, all calculations, I minus 1 and I times a, are done before fact2 is called. And therefore, no stack is needed. Let's now take a closer look at an actual execution. So here above the red line, we have fact1. We will do factorial 10. This gives us 10 times fact1 of 10 minus 1, which is fact1 of 9. So while this fact1 of 9 is being calculated, this 10 times has to stick around. And so we continue. And then fact1 of 9 gives us 9 times fact of 9 minus 1. So the 9 times and the 10 times both have to stick around, and things continue. The fact of 9 minus 1 becomes 8 times fact of 8 minus 1, and so on. And eventually we come up with an enormously long expression, 10 times 9 times 8, etc., times 1 times fact 0. And now we can actually complete. Fact 0 is 1, and then we have this very long multiplication, and then the multiplication is done backwards, piece by piece, and eventually we come up with our answer. So notice that the expression during the execution first grows very big and then reduces in size again. Okay? Now let's take a look at fact 2. So fact 2 starts with fact 2 of 10 minus 1 and 10 times 1, the accumulator. And in the next function body, we have fact 2 of 9 minus 1, and this 10 times 1 comes here, becomes the 10. So we have 9 times 10. And then this 9 times 10 here becomes 90. So we continue, and each time we will take a piece of the previous number and put it in, multiply it with the accumulator, and eventually we come up with fact 2 of 1 minus 1 and 1 times this final result. And this one will be 0, and eventually we come up with the final result. Notice that in the second case here, the expression does not grow. No calculation has to be waiting until something else is done. And that's because of tail recursion. So this expression, we call it a true loop. Okay? Now let's make a small generalization. In the functional paradigm, what we have seen, we can schematicize it like this. As a while function, which takes some state, has a condition for termination, is done, for example, part of it being equal to 0, and then it has a transformation of the state. So this state could be multiple arguments. It could be both the part that's decreasing and increasing, and the transform is going to do one step in the invariant programming where one part decreases, increases together inside of S. Notice that the while here is the last operation, so here we have tail recursion. In an imperative paradigm, a language with multiple assignments, such as Java or C++, we can write things in a very similar way. So here is a function called while loop, taking also a state, and while not is done S, here we have an assignment. Notice that the destructive assignment, assigning again to variable S, the transformed value, this corresponds exactly to the recursive call. So in fact, syntactically, these two solutions are very similar. You could translate one into the other automatically. And in both cases, invariant programming is the key. It is the important design tool that lets you come up with the correct loop in the easiest possible way.